Okay. Can you see my screen?
Yes.
Yes. Yeah. Okay.
Now. Yeah.
Yeah. Okay. It's a folder with the file. Okay. So good morning, everyone. Thank you to be here also today. Today, as Emilio said, I will present a practical demonstration of the VERMEER Cosmolife tool, the tool for the risk assessment of cosmetics. So first of all, I would like to say that, as I mentioned yesterday, these tools are freely available on this website, the Life VERMEER website. There is a new section now, software, because as we mentioned yesterday, we changed something and we moved the software section here within this website. So you can click here for the cosmetic software, and for the other different section, and you can freely download the software. After the download, you have a folder with different files. Indeed, this application is a Java application, so it is mandatory to have Java installed on your computer, and you can use this application on every operative system, so Windows, Mac, Linux, and so on. And you find also a user guide with step-by-step explanation of the use of this tool. So I start with the real demonstration. This is the first screen, the graphical user interface, the first screen of the software, where the end user has to do very simple operation. Indeed, we said yesterday that it is a very simple, user-friendly tool. We developed this tool in order to facilitate the end user. So the first operation is clicking here at the top right, select directory. You will select the directory for the output file. So clicking, for example, on desktop, save. This means that you will find your output file on the desktop of your computer. So very, very simple. Second operation is the selection of the list of the ingredients of interest, the ingredient that you want to assess, to evaluate. So you have to click here, add new ingredient, and will appear this new window where, as Federica explained yesterday, you can add a new ingredient, inserting an inch name or a CAS number or the SMILES. I don't know if I think most of you know what is a SMILES, but just to quickly explain what is a SMILES, is a sort of alphanumeric string that represent the structure of the ingredient. So just to see a very simple example, using the inch name, you can type, for example, simple preservative, sodium benzoate. You have to type the inch name here. Then you can click on the right this magnifying icon, look up by inch, and the software says found one match. This means that the software found a match between this inch name and the inch name within a database implemented within the software. In this software contains internally a database with thousands of chemicals and a lot of information that we will see more in detail which kind of information are implemented within this database. But now clicking here on OK, in this window appears also the CAS number of sodium benzoate and the SMILES. In this case, you have two different SMILES. This is the original SMILES of sodium benzoate. Indeed, sodium benzoate is a salt, so you find also the counter ion sodium in this case. And here you will find the neutral form. Indeed, the software, VERMEER Cosmolife, is not able to process these kind of SMILES, these disconnected SMILES. And it is necessary to have a pure neutral form to proceed with the assessment. So for salt, it is mandatory to neutralize the SMILES. Obviously, the software automatically neutralizes the SMILES. I would like to say that for several kind of substances, for example, similar to salt, mixtures, inorganics, polymers, substances for which the SMICE is not pure and neutral SMICE, but it is a disconnected SMICE. In this case, it is not possible to proceed with the assessment. So basically, the software works with an organic SMICE. Then you have to include here, to enter here, the concentration of the ingredient. For example, we can insert 0.5, then you can click on add ingredient, and the ingredient is now in the list of ingredients. Then you can proceed and you can add other ingredient and create your formulation, your cosmetic formulation, for example. I stop one moment here because one question could be, and if I want to add a list of thousands of ingredients, currently is not possible. This kind of operation is not possible to create an external file with thousands of chemicals and upload this file and assess all these substances, all these ingredients. In this first version, we create this format and we give the possibility to the end user to create a sort of classical, typical cosmetic formulation. So with 10, 15, 20 ingredients. So it is possible to create this formulation, adding one by one these ingredients. Obviously, one of the ideas for the future is possibly to include also this functionality and the possibility to upload an external file with thousands of chemicals and proceed simultaneously all these ingredients. If you want, you can save this ingredient or the list of ingredients that you create here. You can save clicking here, save to file, and then you can create your repository into a folder, and you can clicking here, load from file. You can select one of these, clicking here, you can select one of the formulation that you have saved into the folder. I prepare an example, so one moment Okay, this is the example for today. And you can upload this formulation that you have saved into this repository. And then you can modify this formulation. You can add a new ingredient. You can modify, for example, the concentration of one ingredient, for example, glycerin. If you click on glycerin, you can click on this pencil, modify ingredient, and you can change the concentration, for example. You can put 8 instead of 6. So you can play with the software and create and modify your cosmetic formulation. Then here on this drop-down menu, product type, you can select the product type of interest. You can find here several product types, shower gel, shampoo, body lotion, face cream, and so on. You can select one of them, for example, body lotion. This means that you select an exposure scenario for this specific product type. In this case, an exposure scenario specific for body lotion. This is possible because we implemented within the software a list of exposure parameters, such as the time of exposure, the area of application, the retention factor. So the software is able to recognize if the product type is a leave-on, as a body lotion, or a rinse-off, for example, a shampoo. Then a new functionality of the tool is the possibility to select the target population. You know, basically the principal, the main target is the adult, 60 kilograms, but you can select other kind of target population, for example, 14, 18 years, and so on, till a newborn. So can select now adult 60 kilograms. So the input operation are pretty much finished. So as you can see, it's very, very simple to use the tool. And then you have to simply click here on Run Calculation, and the software starts the elaboration and the assessment of this list of ingredients that you prepare here in this input mask. And in a few seconds, you will find these, you will obtain this preliminary output table, this output file. In this preliminary output file, there is the list of ingredients that you selected before in the input mask, with some information related to the hazard, for example, mutagenicity and skin sensitization, the percentage of absorption, the calculation of the margin of safety, and the assessment based on the TTC. Then if you click here on the left, details or PDF, you can open a different file with a detailed report for each ingredient, with detailed information related for this ingredient that you have selected in the input file. Before proceeding with the detailed report, I want to give you some indication of this preliminary output table. For example, you can see here for the hazard, mutagenicity, and skin sensitization, that if an experimental value is present, the software provides this experimental value. Otherwise, the software provides a prediction using one of the in silico, the QSAR models implemented within this software. For the prediction, the software provides also the reliability. There is an indication of the reliability of this prediction. This reliability is based on a parameter called applicability domain index, and the reliability is divided in 3 levels depending on the value of this applicability domain index. We can have a good reliability for the prediction, moderate reliability, or as in this case, low reliability. So 3 different levels of reliability, and it is a very important information to understand the reliability of this prediction provided by the model. Then we try to help more the end user, introducing also different colors, a color specific for the experimental value. And for example, in this case where we have a good assessment, so non-mutagen, non-toxic compound, we have this green for experimental value and faded green for good reliability or moderate reliability prediction. So different colors to discriminate the different assessment for experimental value or the reliability based on the prediction. So green, basically simple to understand, is for good assessment when we have a non-mutagen or non-sensitizer compound. Red for a bad assessment when we have a toxic sensitizer or mutagen or genotoxic compound. Then I proceed now with the detailed report. So I click here. This is the detailed report with all the information. In the first part, there's a sort of summary with the information that you have inserted in the input file, so the name, the gas, the SMILES, the concentration. The software provides also a picture of the structure of this molecule. Then a summary of the exposure parameters that I mentioned before that the software uses to create the exposure scenario. And then start the real output report. Is divided in 7 sections. Section 1 is related to the regulatory list. So we have information, regulatory information. In particular, this section, the software recognizes if the ingredient is present or not within one of the annexes of the cosmetic regulation. As you can see in this case, the software recognizes sodium benzoate in Annex 5, so the list of preservative allowed in cosmetic products. This is possible because the database that I mentioned before, we work on this database and we create different columns with all this information. So the software is able to recognize this information and provide this information here in this section. So you have the indication of the annex, but also the product type where it's possible to use the ingredient, the maximum concentration for this product type, and other information, for example, opinions drafted by the SCCS. Then we introduce here in this section 1 other regulatory information, for example, information retrieved from the CLP, the Classification, Labeling and Packaging Regulation. So another European regulation, you can say transversal to the European cosmetic regulation. But we started also to include information not only retrieved from European regulation, but other regulation extra Europe. And we start with information of retrieved from the safer chemical ingredient list drafted by the EPA, the Environmental Protection Agency from USA. This list is a list of safer ingredients for a specific use. In this case, sodium benzoate is a safer for the functional use preservative antioxidant. And as I said yesterday, we want to continue to retrieve information from USA, Taiwan, China, Korea, and so on, because our idea is to create in this list a sort of international, you can say, section with information retrieved from different nations, different regulation, in order to give the possibility to the end user to know which is the regulation of these countries, and maybe help also in the import-export activity, for example. So the idea for the afterlife, as I mentioned yesterday, is to complete this section with this new regulatory information. Then section 2 and 3 are sections related to the exposure, the calculation of the exposure. Section 2 for the external exposure, and section 3 for internal exposure. Section 2, very simple, is a very simple equation for the calculation of external exposure. Is an equation retrieved from the SCCS note of guidance, so nothing new. Simple equation, and with this equation implemented within the software, is possible to calculate the external exposure. You will find all these formulas, all these equations into the user guide, and also in the paper published related to VERMEER Cosmolife. Section 3 is more articulated for the calculation of internal exposure. Basically, the focus here is on the calculation of the systemic exposure dose, so as indicated in the SCCS note of guidance. So for the calculation of the systemic exposure dose, we use a sort of tiered approach. The first step is the calculation, considering the oral absorption, using 100% of absorption. The second step is the calculation of systemic exposure dose using 50% for dermal absorption, as indicated in the SCCS note of guidance. And then we introduce a new step to refine, in a certain sense, to refine this estimation of the internal exposure. This new step is based first on the calculation of the KP, the skin permeability coefficient. For the calculation of skin permeability coefficient, we create a very simple QSAR model. Is in a simple equation based on two molecular descriptors. One is molecular weight, and the second one is the log P, the octanol water partition coefficient. So we implemented this equation in VEGA, and we create this model to estimate, to calculate the skin permeability coefficient. Then the second parameter to calculate is the Jmax, the maximum flux of ingredient across the skin. To calculate the Jmax, we have to multiply Kp by water solubility. So another simple calculation, and multiplying Kp and water solubility we can finally obtain Jmax, this maximum flux, an important value, talking about penetration absorption. And as I said before, this equation, you will find this equation in the user guide and in the paper. When we finally get Jmax, we can apply this Croes approach. This approach provided by Robert Croes. According to this approach, if the Jmax value is lower than 0.1 micrograms centimeter square per hour, we have, according to Croes, a low level of absorption equal to 10%. If the Jmax is between 0.1 and 10, we have a medium level of absorption equal to 40%. Finally, with a Jmax higher than 10, we have a high level of absorption equal to 80%. So according to this Croes approach, we can obtain three different levels of absorption with value 10 for low, 40 for medium, and 80 for high absorption. So it's not a definitive way to calculate the real percentage of absorption, but we try to refine these methods in order to have a new possibility to calculate the systemic exposure dose. And as I said yesterday, again, we want to continue. One of the ideas for the afterlife is to refine again this section using, for example, PBPK modeling or differential equation in order to try to calculate the real percentage of absorption and to have so a perfect calculation of the systemic exposure dose. So I proceed now with the section 4. Is related to the hazard characterization identification. We mentioned here, we discussed it yesterday that at the moment we have just a few endpoints. We have mutagenicity, genotoxicity, and skin sensitization. For mutagenicity, we have this model, this QSAR model based on the Ames test, and for genotoxicity, two QSAR models for in vitro micronucleus and chromosomal aberration. For skin sensitization, we have these two models, CSAR and JRC, and we have created ad hoc for this tool a new consensus model. A consensus model is an integration of these two CSAR and JRC model in order to have a unique value for this endpoint. As I said yesterday, as I explained yesterday, we have to include new endpoints for sure. For example, the most important endpoint for the hazard identification characterization of cosmetics are skin irritation and eye irritation. So we will include for sure these two endpoints. I talked yesterday about endocrine disruptors. We have also to consider carcinogenicity, reproductive toxicity. So there's a lot of work to refine, to improve this section for the hazard identification. So the idea for the future, for the afterlife, is to create a complete section in order to have a complete toxicological profile for the ingredient. Then section 5 is the dose response assessment section. So now the idea for this section is based on the pod, the point of departure, as indicated also in the SCCS note of guidance. As point of departure, is possible to use NOEL, LOEL. Now benchmark dose is one of the new frontier for this dose response assessment section. At the moment, we focus the attention in the software with NOEL. We have in the database data for NOEL, so the software uses an experimental value if it is present, or a predicted value using the in silico model for NOEL implemented within the software. Also for this section, as I said yesterday, we have developed new models for NOEL and for LOEL, also focused on the organ-specific toxicity. So in the future, the idea is to implement new models, better models, and maybe focus the attention on also on the organ-specific toxicity. So implement also this model for NOEL and LOEL specific for liver or kidney toxicity. Then section 6 is the section related to risk characterization. So as you know, for cosmetics, the risk characterization is based on the calculation of the MOS, and the MOS, the margin of safety. Margin of safety is the ratio between the pod, the point of departure, in this case, NOEL, and the systemic exposure dose. And to be considered safe, an ingredient, the value of the MOS has to be higher than 100. In this case, you can see, for example, in 2 cases for 100% and 80%, the value is lower than 100. So this doesn't mean that the ingredient is not safe. You have to consider the different variables. For example, you can see that the NOEL in this case is quite low for sodium benzoate. Maybe there is an underestimation of the real value of the NOEL. Indeed, the reliability of the model is moderate. So the risk assessor has to consider all these aspects for the reasoning for the final decision making. Maybe you can proceed also modifying the concentration of the ingredient in order to better set up this value. So there is a lot of consideration to do for a complete risk assessment. Then we include at the end also a final section for the TTC assessment. I think you know TTC is the threshold of toxicological concern. The threshold of toxicological concern basically is this value for which if you have an exposure lower than this threshold, we can consider that there will be no appreciable risk for human health. This is the main definition of TTC. For TTC, into this software, we use the Kramer decision tree. The Kramer decision tree, developed by Kramer in the 1976, is a decision tree based on 33 questions, which yes or no answer, and a final classification into 3 different classes. Class 1 with a low level of concern, class 2 with an intermediate level of concern, and class 3 with a high level of concern. As I said before, yesterday, we modified this classification because now, according to the SCCS note of guidance, there is a new indication for this approach. We have now not 3 classes, but just 2, class 1 and class 3. Class 2 is incorporated within class 3. And there are new thresholds for this class 1 and class 3. So we refine this tool, including this new approach with this new class and this new threshold. Then the software basically compares the TTC threshold with the exposure previously calculated. So there's a comparison of these 2 workflows. And if the exposure is lower than the TTC, so we can consider that this approach works for this ingredient. Otherwise, as in this case, if the exposure is higher than the TTC threshold, we can say that the ingredient failed, is not past this TTC approach. Obviously, as in this case, you have to evaluate carefully this assessment. You have to consider which is the ingredient that you evaluate with this assessment. You know, generally, you can use TTC for the evaluation of impurities, for example. So ingredient with a very low concentration. If you use a TTC for an ingredient at 8%, obviously it's not possible to use this to use this approach. Then you have to consider that TTC, you can use the TTC assessment at the end of all the risk assessment, just to add another evidence in your risk assessment, but you can use TTC, for example, at the beginning of the assessment, just to consider a sort of prioritization, and then based on the data, the value that you obtained with the TTC, you can proceed with the other steps of risk assessment. So the software provided all the information for all the steps of a risk assessment, but basically it's important to remind that it's up to the risk assessor understand how to use, how to interpret all these results. It's up to risk assessor understand how to interpret all, for example, the result of the models, the prediction of the models, because not always this value is, as I say, the real, the concrete value. You have to maybe search for other values. So basically the software provides all the possible data, but the risk assessor has to interpret very well all this data. And again, as I mentioned yesterday and today, surely we have to improve, to refine. We have a lot of work to do. As I shown yesterday in a slide for the afterlife plan of this tool, we have in the pipeline several new ideas. I mentioned yesterday read across. At the moment, read across is not present here in this software, but for the risk assessment of cosmetics, read across is one of the pillars. Is mandatory in a certain sense to have an approach based on risk read across to have a complete risk assessment of cosmetics. I mentioned yesterday that we focused the attention, for example, for the hazard section on skin sensitization, yes, but on the quantitative risk assessment of skin sensitization. There is a new workflow that we implemented this new in silico workflow for the quantitative risk assessment of skin sensitization. So the software will provide a value, a potency value, and thanks to this potency value, it's possible to create a quantitative risk assessment specific for skin sensitization, similar to the approach focused on systemic toxicity. So there is a lot of new idea, new possibility, new activities, and new functionalities for the future. We have to refine, to work, because it's one of the idea for the afterlife plan. Okay, so I finish my presentation. I hope it's clear.